Hello, everyone. Right, hello, let's start. So today we are talking about the analysis of functions. This is assignment 9, and let's have a look. I'm going to jump straight to analysis of functions. So just a quick reminder: when you're analyzing functions, you want to find the zeros, the intercept, the asymptotes. Yes, is everyone familiar with asymptotes? They could be horizontal, vertical, and slant. Is everyone familiar with all three types of asymptotes? Please let me know in the chat. Okay. Stationary points. Stationary points is where you have a maximum or a minimum. That's where a stationary point is where the derivative is 0. Monotonic intervals. Monotonic intervals is where the derivative has a constant sign. So for example, I can see that here between these two stationary points, let's call them x, a and b, between a and b, the derivative is negative because the graph is slanting downwards. The gradient is negative. We call it, so AB is a monotonic interval. Right, so that means the function is always going up or always going down. Inflection points, that's a point here. That's where the graph stops behaving like this and starts behaving like this. Right, a concave becomes a convex graph. Domain and range. I hope everyone's familiar with domain and range. Right? Any questions? So when you are given with a task to analyze a function, this is what you need to do. You don't have to do all of them, but all those that are that can be found. For example, this graph doesn't have any asymptotes, so we wouldn't try to find the asymptotes. It does have stationary points. Okay, so what I'm going to do here is first I'm going to find the zeros. And I'm going to use red. So zeros. To find the zeros, I just make it equal to 0. So 2x cubed x squared minus 1 equals 0. So I can immediately see that x equals 1 is a solution. What are the other solutions? Well, to find the other solutions, I can either use long division to divide by x minus 1, or I can factor out x minus 1. That's what I'm going to do. I'm going to factor out. So I'm going to write 2x cubed minus 2x squared plus 5x squared minus, that doesn't make any sense. Y, of course, no, sorry. X equals minus 1 is a solution. I'm going to factor out x plus 1. x equals -1 is a solution. So 2x cubed plus 2x squared plus x squared minus plus x minus 1 equals 0. And 2x squared x plus 1 plus x plus 1 and minus x plus 1 equals 0. X plus 1, 2x squared plus x minus 1 equals 0. So here I can find the factors. So x equals -1 is a solution again. So it's going to be x plus 1 squared multiplied by 2x minus 1, I believe. 2x squared minus x plus 2x minus x, yeah, equals 0. So zeros are zeros is x equals -1, x equals 1/2. You can kind of already draw the graph, right? That's what you've been taught at A level. Okay, so then I find the stationary points. I find the derivative. So y prime is 6x squared plus 6x equals 0. So x squared plus x equals 0. X equals 0, x equals -1. So these are the stationary points. And inflection. So y double prime is 12x plus 6 equals 0. X equals -1/2 is an inflection point. Okay, asymptotes none. Stationary points. Okay. Now there are many different ways you can do that. I'll show you the way I was taught and the way I prefer using. So you draw a number line x, and you put all the interesting points. So -1, 0, -1/2, 1/2. So -1, -1/2, 0, and then 0, then what else? 0 and 1/2. All right. So first of all, we're going to determine whether the function is positive or negative. So above the x-axis or below. So we will use the method of intervals. And we'll look here. So if basically we want to know whether the function is positive or negative. So this sign. So kind of don't even need just say, okay, so f of x, f prime of x, f double prime of x. Okay, so we found the interesting points. So anything that happens, anything interesting that happens between these points. All right, so the function itself, we need to work out where it's positive, where it's negative. What we did, we factorized it. So if x is greater than 1/2, the function is certainly positive, because why wouldn't it be? Okay, if you substitute a number which is greater than a half, and it will be a positive value. So f of x is positive. Between 0 and 1/2, it is going to be negative, because 1/2 is 0. Now, 0 is not a 0. That's funny. So it stays negative. At 1/2, a minus 1/2, nothing happens either. So it's still negative. And at beyond -1, well, you can see that if you substitute, let's say -3 into this expression, it was going to be negative again. So the graph is negative, 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 positive. It only crosses the axis at 1/2. All right, the derivative. You can see that the derivative is this, and it is positive here, positive, negative, negative, positive. So that means that the function is increasing, decreasing, decreasing, increasing, increasing. Okay. So the derivative tells you whether the function goes up or down. And the second derivative, finally, is this. So it's going to be negative, negative, positive, positive, positive. Okay. And then here, I kind of draw the behavior of the graph. So what I'm doing. So the function is positive, so it's above the x-axis. It has a positive gradient, and it has a positive second derivative. That means it is a convex function. So the function would look like this. Function is increasing. It is curved like this. It is increasing. It is curved like this. And it's positive. That means it is above the x-axis. Here, the function is below the x-axis, but it's still positive. It's growing, and it's convex. So it's going to be below the x-axis, but it's like this. Okay. The function is negative, so it's below the x-axis. It is growing. However, the second, it is it's decreasing, but the second derivative is still positive, so it's like this. Here, the function is negative. It is below, it is decreasing, and it is concave. So it's like this. And then finally, negative, growing, concave. All right. So I kind of got a good idea of what the function looks like just by drawing these arrows. All I need is to find the values at these 4 interesting points, and then sketch the graph. I mean, look, for a cubic graph, it is an overkill. It is a severe overkill. But that's the process. I'm demonstrating the process. I'm not demonstrating how I would solve this particular problem. Okay, I hope that makes sense. Everyone's been quiet, so give me some feedback on. Do you understand everything? What I'm doing? Do you understand the method? So you draw the points. So 0, 1/2, minus 1/2, minus 1. Okay, so 0. If you substitute 0, it's going to be -1. 0 is -1. 1/2 is 1/2 is a 0, isn't it? Yes, it is a 0. Minus 1/2, that's an inflection point. So I need to substitute minus 1/2. And that's where it gets tricky. If you're doing it without a calculator, substituting minus 1/2 into this equation is not the best thing, but okay, I have to do it. So y of 1/2 is 0. Y of 0 is -1. Y of -1/2 is going to be 2 multiplied by -1/8 plus 3/4 -1. So that's -2 -1/4. 1/4 plus 3/4 -1. So that is 1/2 -1 -1/2. So it's somewhere here. And y of -1 is 0. Okay, so now following this sketch, I can see that the graph goes like this, up to 0. That's a maximum. This is a minimum. And I go like this. It's a minimum. This is like this. Now, at A level, you were taught how to draw these graphs, right? However, this method works for any graph, not just a cubic graph. All right. Do you understand the method on a scale of 0 to 10, please? Oh, there's more people now. Do you understand the method on a scale of 0 to 10? Let's double check. Y equals 2x cubed plus 3x squared minus 1. And you can see that indeed graph does look like that. Just 2 of you? There's at least 9. There's 9 people here. Can I get an answer from everyone, please? Asymptotes. Asymptotes is a separate thing. To find an asymptote, you need to find the limit so finding asymptotes. I'll demonstrate finding asymptotes on problem 3. Okay. Problem 2. Well, it's the same. It's the same principle. Would you like me to do problem 2 or skip to problem 3? Please let me know. Okay, lovely. Problem 3. So, okay, there are 3 types of asymptotes, and we have to find them separately. Okay. So first, horizontal asymptotes. Horizontal asymptotes. Horizontal asymptotes. What you need to do is find the limit as x tends to infinity. Separately, plus infinity and minus infinity. X tends to infinity of 2 divided by 1 plus x squared. And as you can see, as x tends to plus infinity, this becomes, what's the limit? 0. Yes, of course, it's 2 divided by 1 plus infinity squared. So 1 plus infinity squared is infinity. 2 divided by infinity is 0. And now you find the limit as x tends to minus infinity, and similarly, the answer is also 0. You could save yourself time and just put plus minus, but it's not always the same. It's sometimes different. And that means that y equals 0 is a horizontal asymptote. On left and on right. Okay. Vertical asymptotes occur when the denominator is 0. Denominator is 0. But it doesn't. So 1 plus x squared equals 0 has no solutions. No solutions. That means there's no vertical asymptotes. Okay, and slant asymptotes. There's no indication that there will be a slant asymptote. Okay, a slant asymptote occurs. Slant asymptote occurs when the limit of x tends to plus minus infinity of f of x divided by x is finite, is a real number. Okay, let's put it, if f of x divided by x is a real number, in this case it is not, because if you divide f of x no, it's not. It's a non-zero. It's a non-zero non-zero and real. So it's a real number between. It's a real non-zero number. Okay, sorry. F of x divided by x is going to be 2 divided by x, 1 plus x squared. And clearly that tends to 0 as x tends to infinity. As x tends to plus minus infinity. So there's no slant asymptotes. No slant asymptotes. So with this method, you would use this separate and then draw the asymptotes separately. So it's just like an addition. It's a separate addition on the for this method. Okay, so very quickly I find the zeros. Zeros, none. There are no zeros here. Intercept, the y-intercept is 2. Y equals 2. And then the derivative is, what's the best way to find the derivative? Not the quotient rule, clearly. It's going to be 2 multiplied by x plus, what am I doing? 2 open bracket 1 plus x squared to the power minus 1. So chain rule, I'm guessing, chain rule. So minus 2 multiplied by 1 plus x squared to the power minus 2. Multiplied by 2x, of course. Okay, that makes more sense. So that is minus 4x, 1 plus x squared. Okay, so the stationary point, x equals 0, because this is 0 when x is 0. Stationary point is x equals 0. That's good. And then the second derivative, we find, well, we got to use the quotient rule now. minus 4 multiplied by 1 plus x squared squared minus plus 4x multiplied by 2, 1 plus x squared to the power 1 multiplied by 2x over 1 plus x squared to the power 4. All right, that's not a pleasant thing to do, but we can simplify that. So that becomes 3. So this becomes minus 4 minus 4x squared plus 16 x squared divided by 1 plus x squared cubed. That's equal to 12x squared minus 4 1 plus x squared cubed. So that's equal to 0 when x squared is 1/3. So x equals plus minus square root of 1 plus minus 1 over square root 3. These are inflection points. Inflection points. Okay. And then we quickly draw the table and put the interesting points. So minus 1 over root 3, 0, 1 over root 3. The function is always positive. So positive, 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 because it can't be negative. Then the derivative is positive, positive. Yeah, we're looking at this, positive, positive, then negative, negative. And then the second derivative is okay, it's positive. It's positive, so it's like this. Then it is like this, then like this, then like this. So positive, positive, negative, negative, positive. Just looking at this expression. All right, so now we can draw these. It's going to be above. So it's going to be like this, then like this, then like this, then like this. So this is clearly a maximum point, and this is a point of inflection. And then when you draw the graph, sketch the graph. So you have 0, 2, 0, 2. That's the maximum point. Minus 1 over root 3. Minus 1 over root 3, that's what? 1 over root 3. Just over a half. 0.6-ish. Okay, so here and here. You can, depending on what you need to do, you can substitute 1 plus 1/3. That's 4/3. 2 divided by 4/3. So 1 divided by 2/3, 3 over 2, 1.5. 1.5. 1.5. Here and here. And those are the points of inflection. Okay, beautiful. So, and finally, the asymptote. We found the asymptote and it said y equals 0. It's an asymptote on the left and on the right. That's important to remember because you can have a different asymptote on the left and on the right. Okay. Okay. And y equals 0. That's your asymptote. And now just draw. And double check. Y equals derivative 2 divided by 1 x squared. Here we are. All right. So we got it. I mean, I'm not as fast as Desmos, but I think I did a decent job here. Okay, so the next one, well, same principles apply. So let's, I'll try to do it quickly as I would normally do it, without not taking shortcuts, but just, yeah. So find the zeros. So zeros. Oh, interesting. So we immediately see that there's a vertical asymptote here. Okay, so zeros. X equals 3. That's a 0. Right? I hope everyone can see that. X equals 0. Domain X is not equal to 0. Range. Well, we can clearly see it's a square number divided by square number. So it can be only be positive or 0. It clearly cannot be 0 because if you substitute 0, that's going to be well, we can't divide by 0. So is there a minimum value though? Oh, it can be 0 if we, sorry, if the y can be 0. Can it be anything but, yeah, pretty much. So y is greater or equal to 0. I'm pretty confident with that. Okay. That's good. That's good. Now x equals 0, if you substitute 0, yeah, okay. 0s, then you find the derivative. Find the derivative. I'm first going to simplify the. That doesn't make any sense. No, that's fine. Find the derivative. So it's going to be. I'm using the chain rule, quotient rule here. Sorry. So 2x minus 3 multiplied by x squared minus x minus 3 squared multiplied by 2x divided by x to the power 4. I can simplify. This is 3. It's going to be 2x squared minus 6x minus 2x squared plus plus 6 multiplied by 2, 12x minus 9 times 2, 18. 18 divided by x cubed. So, interestingly, this cancels. We've got 12, 6x minus 18 divided by x cubed. So stationary points. points is x equals 3 again. Okay. Next, x equals 3. The second derivative, we differentiate that. It's going to be 6 multiplied by x cubed minus 6x minus 18 multiplied by 3x squared over x to the power 6. So 6x cubed minus, so 6 times 3, 18, 18x cubed plus, okay, let's simplify. Squared 4. So that is going to be x to the power 4. 6x minus 18x squared minus 54x plus 54x is equal to 6 plus 54, 60, 60x minus 18x squared divided by x to the power 4. That's equal to 0 when, so inflection, we have x equals 0 and x equals 60 over 18. 60 over 18, which is 10 over 3, 10 thirds. Okay. So 0 and 10 thirds are the points of inflection. What else? Asymptotes. Okay, interesting. Asymptotes. Well, x equals 0 is clearly a vertical asymptote. Horizontal. Okay, so vertical, horizontal. We find the limit of, as x tends to plus infinity, of x minus 3 squared divided by x squared. So how do we deal with limits like this? We expand. So it's going to be limit as x squared minus 6x plus 9 over x squared. Now we divide to plus infinity, and that's equal to limit x tends to plus infinity of 1 minus 6 over x plus 9 over x squared. Now, as you can see, this, as x tends to infinity, this becomes 0, and this becomes 0 again. 6 divided by infinity is 0, 9 divided by infinity is 0. So this tends to 0, this tends to 0. So we're left with 1. So the limit is 1. And interestingly, if you do minus infinity, also the same thing. So you can just put plus minus here. Okay, slant asymptote. The limit of x tends to infinity of x minus 3 squared over x cubed, because we divide by x, is clearly 0. Yeah, you don't even, you kind of understand that x squared divided by x cubed will lead to 0. So no slant asymptote. All right, so the horizontal asymptote is y equals 1. Y equals 1 is the asymptote. Left and right. Okay, lovely. Moving on. Okay, there's still 10 people in. That's good. That means people are still listening, hopefully. Okay. That's moving on. All right, so do we need a table? Yeah, we need a table. Well, first of all, let's draw what we have so far. Then this is x, this is y. So let's have y equals 1. That's an asymptote on the right and on the left as well. Then we have the vertical asymptote is x equals 0 is a vertical asymptote. Okay. We have a 0, which is x equals 3, 1, 2, 3. It's a 0. We have the graph is positive. Aha, interesting. The graph is positive, and this is a vertical asymptote. So the graph only exists in the top half. And inflection, x equals 0 is an inflection point. But 0 is not in the domain. Okay, so that's not an inflection point. Apologies. 10/3 is an inflection point. So 10/3 at 3.3. So 10/3, that's an inflection point. Okay, like this. 10/3. So that's 3. That's 10/3. That's an inflection point. What is the value? 10/3 minus 3, so that's 1/3 divided by 10/3. 10 divided by 81. Wow, that's 0. So it's really close here. Ah, okay, that's starting to make sense to me now. All right. Okay, so we found that's the inflection point. That's a stationary point, probably a minimum. So what we do is we draw the table. So that's 0, 3, 10/3. Those are the interesting points. So we start with f of x, and f double prime of x. We draw a table. Okay. Does it make any sense? Like this. Okay. The function itself. Yeah, I canceled out the x squared. That's why I got I did, but still, there's no excuse. I mean, I should have seen that there's an x in the denominator. I shouldn't have. There's no excuse that saying that x equals 0 is a point of inflection. It can't be a point of inflection because the function doesn't exist and the derivative doesn't exist. Okay, so we've established that the function is always positive, 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 positive. And then the derivative is up to 3. It's negative. Oh no. So the derivative is here, this one. And you can see that it changes sign twice. So it's positive when x is greater than 10/3, it's going to be positive. Between 3 and 10/3, it's still going to be positive. Between 0 and 3 is going to be negative. And between minus infinity and 0, it's going to be positive. So this is how the graph looks like. So it's increasing, decreasing, increasing, decreasing. Oh, sorry, increasing, increasing. Then the second derivative is this thing. So there we have 2 points where the sign changes, 0. So that's going to be negative, positive, positive, negative. So basically the function. So what I did, I just substituted any value from the interval. Sorry, does everyone understand why I put minus, plus, plus, minus? Please let me know if you don't, because I assume that you understand. If you don't, I just need to explain it. It won't take, doesn't take a lot of time. Please let me know. It's a little less enthusiasm than I've hoped for. Does everyone understand? Are you sure? I'm happy to explain. It's not a problem for me. In that interval, yes. So you take any value from the interval and you substitute that in. That's how you know it's positive or negative. Another way of doing it is solving an inequality, but it's the same. It's the same idea. Okay, so right, and that means that the function is concave, convex, convex, concave. I always get them confused. So if I sometimes say concave when it's convex, apologies. Okay, so function is positive. It is concave. That doesn't make any sense. Doesn't make any sense. Concave, yes. Convex, convex, convex. Six x 6 multiplied by x cubed minus 6x minus 18 multiplied by 3x squared. So divide by, so 6x minus 18x squared plus 54x. 60x squared. That's somewhat bizarre. I understand very well how the function looks like on the right, but I have trouble visualizing it on the left. y equals 1 is an asymptote. Okay. Y equals 1. Then should be approaching from the top, from the bottom. Yeah. It should be minus 18x. What do you mean? I think that's a... Oh, I see. Yes, I canceled x squared. So it should be like this. Yes. 54. Thank you. Okay, 54. Right. So that's 54 minus plus 6x minus 18x squared. Eighteen x. Yes, thank you. 64, 6x minus 18x. So that is minus 12x plus 54. So x equals 54 over 12. 54 over 12, that is divided by 6. That's 9 over 2, 4.5. Okay, that's a more reasonable value. 4.5. So this selection is 4.5. Okay, 4.5. 4.5. That's the inflection point. And here, 4.5. That's negative, positive, positive, positive. Yeah. Okay, perfect. There's no inflection points here. Okay, good. So here it's the function is positive, the gradient is positive, and the function is convex. So it's going to go like this. From 0 to 3, it is a decreasing function, like this. From 3 to 4.5, it is an increasing convex. And from 4.5 to infinity, that's increasing concave. So you can see that this is a point of inflection. This would be a point of maximum, but maximum doesn't work like this. And especially 0 is an asymptote. So it's going up, going down. All right, so we can draw the graph. So from here, it's going like this, asymptote. Then from 0 to 3, so it goes like this, all the way down to 3. So from 3 to 4.5, inflection, and then going like this towards the graph. Lovely. Thank you, Kaden. And let's check. Y equals x minus 3 squared over x squared. Yeah. I think that's even less dramatic than what I've drawn because it doesn't show you the asymptote. So I'm just show you the asymptote equals 1. Here's the asymptote. Okay. Very useful skill to be able to predict the behavior of graphs. That's sort of what we're doing. We're predicting the behavior of functions based on what we know. This is called analysis, mathematical analysis. Like we have, look, calculus in many countries is called mathematical analysis or analysis of functions. So this is yeah. Good, good. They're not exactly the same, of course. They're not exactly the same, but yet, yeah. Another one. This has a slant asymptote. Now, how can you spot a slant asymptote? Is when the power in the numerator is higher than the power in the denominator by exactly 1. Slant asymptote, when the power of numerator is equal to the power of denominator plus 1. This is a 2, by the way. Apologies for the rubbish. So the top has a power of 3, and the bottom has a power of 2. And that indicates, that's an indicator that there's going to be a slant asymptote. The easiest way to find the slant asymptote, so how to finding a slant asymptote. If you were programming a computer, then you would use this method. So the universal method, straightforward method. Theoretically, you could have, yeah, asymptote can be of any shape, but we're not really interested in quadratic asymptotes. Yeah. So straightforward word method. Okay. I hate this method, honestly, but I'll show you too. Straightforward method. I hate it because it takes all the fun out of maths. Straightforward method. So what you need to do is suppose you have a slant asymptote, and the slant asymptote is y equals mx plus c. Is your slant asymptote. Suppose is a slant asymptote. Then m is going to be the limit as x tends to infinity plus infinity of f of x divided by x. And then c is going to be the limit of x tends to plus infinity of f of x minus mx. I think that's it. Let's test. Let's test this method. Right, so I'm going to take this function, divide by x. So it's going to be x squared. It's going to be the limit x squared x minus 1 divided by x plus 1 squared. X tends to infinity. So we simplify. It's going to be x squared minus x divided by x squared plus 2x plus 1. We're going to divide top and bottom by x squared. Divide by x squared top and bottom. So it's going to be 1 minus 1 over x. And here it's going to be 1 plus 2 over x plus 1 over x squared. And because it's the limit as x tends to infinity, limit as x tends to infinity, that means it is, well, this tends to 0. This tends to 0. We've got limit of 1 over 1, so it's 1. And you can see that it works for both positive and negative. And that means that m is 1. We found the gradient of the slant asymptote. Then we'd find this limit. So c is the limit of x tends to plus infinity. I'm doing plus infinity first. And I'm going to do x squared x minus 1 divided by x plus 1 squared minus 1x minus x. So it's the limit of x tends to plus infinity. X cubed minus x squared minus good question, Sanjibati. Why is the gradient of the asymptote is the limit of this over that? It's kind of, I mean, you could prove it mathematically, but as a physicist, you are finding how many times the function is greater than y equals x. Basically, what you're doing here, and that's the physicist in me speaking, what you're doing here is how many times is f of x is greater than y equals x. Yeah, because that's what you're doing. And let's say m is 3. That means that f of x behaves like y equals 3x. Does that make sense? Or you could say, if if m equals y equals mx is the gradient of the asymptote. So you can say that f of x is approximately mx plus something, right? And then f of x divided by x is going to be approximately m plus something over x. And as x tends to infinity, this becomes 0. I hope that makes more sense. Okay. Basically, we're saying that f of x is really close to mx. Is really close to mx. So yeah, that's what we call asymptotic behavior. Okay, so then we find this. So x cubed minus x squared minus x cubed minus 2x squared minus x over x plus 1 squared. What can we do here? So cubed cancels. We're left with x squared minus 3x squared, limit minus 3x squared minus x divided by x squared plus 2x plus 1. X tends to infinity. And once again, we divide top and bottom by x squared. We get minus 3 minus 1 over x. And here we have 1 plus 2 over x plus 1 over x squared. X tends to infinity. And we can see that this tends to 0, this tends to 0, this tends to 0. It's minus 3 over 1, so it's minus 3. And once again, it's plus or minus, because it doesn't matter plus or minus, you would have the same result. And that means that C is equal to minus 3. That's how you find the slant asymptote. I don't know how about you, but this method is so unalive. It's just following a recipe, which doesn't give me any satisfaction. That's what I'm trying to say. I'll show you a different way, which you might have been taught in school, how to do the other method, which is much easier. So you found the slant asymptote. You found the slant asymptote using two formulas, and then you just apply the same method. So you find the derivative, you find the zeros. So domain x is not equal to minus 1. Range what can you say about range? Well, squared positive. Can it be 0? Yes, it can. It seems like there's no limits for the range. Y is any real number, but I'll put a question mark because I'm not 100% sure. I'm not satisfied with this. What do I see? So I see it's x squared, x minus 1. So you can't have minus 1. But then this is a positive, and this could be positive or negative. So theoretically, could be anything. Okay, let's see what we arrive at when we start finding the stationary points. Okay, so we find zeros. Zeros is pretty easy. It's already factorized. So 1 and 0. X equals 0, x equals 1. Then we find the derivative. Find the derivative. Should I just write it down here? X squared. I'm going to expand it. So it's going to be x cubed minus x squared divided by x plus 1 squared. Not that it makes life much easier, but x cubed. The derivative, so it's going to be 3x squared minus 2x multiplied by x plus 1 squared minus, we're using the quotient rule again, x plus 1 to the power 4, x cubed minus x squared multiplied by 2 x plus 1. So x plus 1 cancels. Okay, what are we left with? We're left with pretty, okay. 3x cubed plus 3x squared minus 2x squared minus 2x minus 2x cubed plus 2x squared plus 1 cubed. What's this out? That's about it. Okay, so it's going to be x cubed plus 3x squared minus 2x, x plus 1 cubed. So that is x squared plus 3x minus 2. Okay, x plus 1 cubed. It's not too bad. And x minus because it's not factorized. I made him an error. Minus 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 plus. Okay, let's assume I haven't made an error. It means it doesn't factorize. So we just keep it like this. So the stationary points. Stationary points is x equals 0. That's the only stationary point. Okay, inflection. I'm kind of dreading find the points of inflection because it's going to be something really awkward. Okay, but I'll just put a question mark here. I don't want to do something that will take a long time. So maybe I can do without. Maybe I can do without and predict any inflection points, if that makes sense. We already have slant asymptotes, which gives us a lot of information about the graph. Okay, so x, we have well, we have 0, and x equals 1. Okay, 0, 1. we can see that the graph is f of x, f prime x at 1. Okay, so the derivative, so it's going to be positive, negative, negative. That's the graph. Then the derivative is going to be positive, positive, negative. Well, I think we can work with that. All right, so the function is positive and growing, so it's like this. Well, we don't know the second derivative. We can assume the second derivative, but we don't know it. A function is negative but growing, and here the function is negative and decreasing. Okay, and yeah, so let's can I use them. So we start with the asymptote. The asymptote is 1 x minus 3. So x minus 3 is an asymptote. Y equals x minus 3. Then x equals, then x equals minus 1 is an asymptote. X equals minus 1 is an asymptote. Minus 1. Okay. Right. Zeros are 0 and 1. 0 and 1. And the stationary point is 0. Maybe 0 is not a stationary point. But it is. Doesn't make any sense. Okay, let's see what else we can do. Then we have oh, we forgot minus 1. We've got to add minus 1 here. Minus 1. We have the derivative is going to be positive. It's not going to be negative. So it's going to be like this. Okay, so something's weird going on here. Not sure exactly what, but I can certainly draw this part of the graph. What's going on? Might have made a mistake because it doesn't make sense to have. You can't have two zeros, one being a point. So x equals -1. Okay, so the one on the left. -1. Decreasing until increasing. Doesn't make any sense. Decreasing, increasing, increasing. So it looks like the graph would be like this. Should be like this. And like this. All right, I'll have to draw it. I made a mistake somewhere. Let's see where. X squared y equals x squared x -1. Yes, horizontal and slant asymptotes mutually exclusive, certainly. -1 and x plus 1 squared. X plus 1. No, you could have, sorry, you could have a horizontal asymptote on the left and a slant asymptote on the right. Yes, you can have that. Whoa. Of course, the function is negative. Function is negative, positive, negative, negative. Ah, of course. Yeah, that makes sense. Okay. All right. No, looks like I haven't made a mistake. I just couldn't interpret it correctly. So this is a this is a 0. So the function goes like this. Then it crosses the x-axis, then it goes up, touches the y, and then goes down. And that corresponds to here. Except this one is positive. Okay, well, no, I have made a mistake here. And then here, it is like this. think I made a mistake with the first derivative. Okay, I'll need to. Oh, I haven't made a mistake here, but I've made a mistake here, so I'll just put a question mark here. Right. But I won't redo this. Apologies. So just let's pretend this never happened. I think you got the point. There was more than one solution for the stationary point. There must have been. Yeah, there's 3 stationary points. And so I must have made a mistake here. There are 3 stationary points. So, but I failed to find them. I found only one, which is x, which is 0. Okay. The last thing, well, I think you know these pretty well. I mean, the working was correct, but how could it be correct? This has no solutions. X squared plus 3x minus 2. The discriminant is negative. B squared minus 4. Okay. Apologies. Okay. Of course. Of course. 9 minus 8, or 9 plus 8 is positive. Square root of 17. Yes, it has the same stationary point. So this is correct. This is incorrect. I did not find the stationary points correctly. Points x equals 0 and x equals minus 3 on 2 plus minus 3 on 2. That's what? 3 over 2, 9 over 4. 9, that's 9 over 4 minus 17. Square root of 17 over 2. I think that's about it. Okay. Which gives us 2 more stationary points. And then you do of x, you get 0, you get minus 1, you get, is 1 a thing? Yeah, 1 is a thing. 1, this is minus 3 over 2, minus 3 on 2, plus root 17 over 2. And this is minus 3 on 2 minus root 17 over 2. And then you get the graph that looks like this. 0.56. Yes. Okay. Right, the last thing. Well, you probably know how to do these. I'm just going to quickly sketch those. Oh, you know what? I'm going to copy this. 8 times? 1, 2, 3, 4, 5, 6, 7, 8. Okay. The modulus of x simply flips the bottom of the graph, the negative part of the graph upwards. So the graph would look like this. This is A. For B, it is the modulus of x. So the modulus of x takes the right-hand side and mirrors it onto the left. So the graph becomes an even graph. The modulus of a modulus, so you do both. So first you do this, and then you do it like this. Okay. And f of x plus 1, that's simply shift to the left. So that's like this. Easy. F of 2x, that is a stretch, horizontal stretch, so that it goes like this, becomes narrower. Okay, so C, D, E, F, 2x plus 1. Now that's a tricky one. So you could rewrite it as f of 2x plus 1/2. So that means you stretch it you make it narrower, and then you shift it. Yes, you make it narrower, and then you shift it by 1/2. So first you do this, and then you shift it by 1/2 to the left. So it goes like this. For x plus 1, that's the easiest one. You just shift it upwards, easy, and to 2f of x. So you stretch it vertically and move up. So stretch it vertically and then shift it up by 1. Okay, I won't go through that. That's probably the easiest one. Just a quick reminder for you. And I'll stop here. I hope that was useful, and I'll see you. I might not see you next week. I've got an event coming up on Wednesday. Well, apologies that it's been last week was an event, next week's an event. No, sorry. I have covered. Next week I have somebody else to cover for me. So yeah, you will have you will have a session next week. Sorry, I've completely forgot. All right, see you then. You're welcome. Bye.